We're going to look at an interesting problem today, and that's a really understanding and using the buoyancy force problem. So this is an interesting example. So say we suspend a block of gold, and we're going to submerge it into water. Before we submerge it into the water, we can measure that the tension on the rope that's suspending it is 45 newtons. And let's assume that the rope is light, so we don't have to account for the rope's mass. So we want to figure out, once the block is fully submerged into the water, how does the tension force on that rope change? So, because it's going to be different. And you can think about this problem, you can actually even try doing this at home with other things, but you're probably already familiar that the tension force is probably going to lessen, right? Because as it gets suspended in the water, there's a force that kind of pushes it upwards, and that is called the buoyancy force. And so we're going to calculate that and figure out how it affects the tension. So in order to do this, we need to know three equations. We need to know that the tension force is equal to the mass times the gravitational acceleration. And this is going to be on the string before it's submerged into the water. We need to know that the density of an object is equal to its mass divided by its volume. And we need to know the equation for the buoyancy force is going to be equal to the negative that is there to show it's an opposing force, the density of what it's being submerged into. So in this case, it's the water. I'm going to write a W for a subscript so we don't mix up our densities. And times the gravitational acceleration times the volume of the object that is being submerged. So in this case, that's the gold. And we're going to be able to figure out what the tension is on the force after it's submerged just using these three equations. But before we do that, I want to show it using a force diagram just to kind of show what's going to happen after it gets submerged. So before it's submerged, a force diagram of this object is going to just have two forces acting on it, right? And if we can say that as we're dropping the block down in, it's neither accelerating nor decelerating, it's going at a constant velocity, so these net forces are going to be equal to 0. So F net equals 0. So the force pulling it down is obviously the force due to gravity, which is the mass times the gravitational acceleration, and then the force holding it up would be the tension of the string, which is where we get this first equation here. So this would be before the block is submerged into the water. After is what we're really interested in. After the block is submerged into the water, we still have a force pulling it down due to gravity, mass times gravity, and that's actually the same force. You get lighter underwater, not because that force has changed, but because the buoyancy force is acting in opposition, and that's due to the density of the water. So you have still the tension force of the string, of the rope pulling it up, and then you've got this third force, and this is the buoyancy force. And this is this difference here. So if I can find another color here, this difference is what we're looking for. This is the tension force after. That's the difference in change. To set this up, we're going to really see that this final tension force is going to be equal to whatever initial tension force I had plus this buoyancy force. And I'm going to have a plus here because the buoyancy force is already taking into account that it's an opposing force, so I don't need to put a minus. I'm given the initial tension force. Now I need to just calculate what is this buoyancy force. Right, so the buoyancy force is the density of the water times the gravitational acceleration and times the the volume of the gold. And we need to figure out what the heck is the volume of the gold. So the next step we're going to do is going to use this rho over mass and volume equation for the density. We're going to rearrange it so instead of being the density is equal to the mass over the volume is equal to the mass over the density. And this is the volume of the gold and the density of the gold and the mass of the gold, because this is what we're trying to figure out. We want the volume of the gold. And we can use this, so all of these are known except for this mass of the gold. We don't know what the mass of the gold is. So in order to find that, we're going to use the fact that the initial tension force T initial is equal to the mass of the gold times the gravitational acceleration. And we can rearrange this so the mass of the gold is equal to the initial tension divided by the gravitational acceleration. And we can plug this in. So we're going to plug this in to this mass up here. So the volume of the gold becomes the initial tension divided by the gravitational acceleration, all divided by the density of the gold, which simplifies to the volume of the gold being the initial tension divided by the gravitational acceleration over the density of the gold. And we're going to use this and plug this in for this volume up here. So the buoyancy force is equal to the negative density of the water. Make sure you don't mix up your subscripts here. The gravitational acceleration, and then instead of writing the volume of the gold, I'm going to write this, what I just calculated it to be. So it's the initial tension divided by the gravitational acceleration and the density of the gold. And you'll notice these gravitational accelerations cancel out, so we didn't actually end up needing it. So that is equal to the negative density of the water times the initial tension divided by the density of the gold. And now we can plug this in for this right up here. So right, we're kind of going all over the place here, but our final tension is going to be that initial tension plus, I'm going to put it all in parentheses, the negative density of water times the initial tension over the density of the gold. And this is going to give us our final tension. So let's actually calculate that. We're going to have to do one more step before we calculate it. Before we actually calculate this, it's a subtle difference, but you might have noticed our units are different. So the density of the gold is given to us in grams per centimeters cubed. The density of the water is in kilogram per meters cubed. That should be a cubed. Now, which one do we use? How do we know which one to use? We're actually going to be using the kilogram per meters cubed because we are given that the tension force is in newtons. Because a newton, 1 Newton is equal to 1 kilogram meter per second squared. And it's this kilogram meter unit that we care about. So in order to apply that gold measurement for density, we actually have to convert it. So we have the density of the gold being 19.3 grams over 1 centimeter cubed. And I call this the railroad track method whenever converting something. You use it a lot in chemistry for stoichiometry. I find it very useful to not mix up your units and to actually get them to convert nice and easily. So what I do is, let's do the grams first. So we have 1,000 grams per 1 kilogram. And anything that is diagonal, we're just going to cross out like that. And then whatever unit I'm left with, if that's what I'm going for, then I've done it right. So because I have kilograms left, I want to stay in kilograms. I don't need to convert this further. But I still need to get rid of the centimeters cubed. So I need to have centimeters cubed up here, and I need to have meters cubed down here. And it is important to note, so to get this correct, so for every 1 meter cubed, I have not just 100 centimeters cubed, I have 100 cubed centimeters cubed. Now it's important to do that, otherwise your unit conversion is going to go off wrong. And this is just because it's raised to the 3rd power. And when I calculate this, I get 1.93 times 10 to the 4. This is kilogram meters cubed. Now that this is the same units, now I can plug everything in and I can calculate what this final tension is going to be. So my final tension is going to be equal to that initial 45 newtons plus the negative density of the water, 997 kilogram meter cubed. I always like to put all my units in the equation because when everything cancels out, if you get the final unit, everything should add correctly. Your units should match, and that's a good way to tell if you've done the algebra correctly. So this is over 45 newtons divided by the density of that gold, which we just calculated as to be the 3 times 10 to the 4 kilogram meters cubed. These units will cancel out. What I'm left with is newtons, and I can add newton to newtons, so I've done it correctly. And what I get is, this should be 42.6, we'll round it up, 8 newtons. So the tension on the string is lighter after the block of gold is submerged into the water, which makes sense if we think about it. If we put the block into the water, there's going to be less tension because that buoyancy force is actually pushing it up.